Hi everyone, so today we're going to expand our knowledge on graphing quadratic functions in intercept form. So intercept form is in the form f of x equals a times x minus p times x minus q. Now notice this is also called factored form, and it's referred to as factored form because it can be written as a product of its factors, which makes it very easy to find its x-intercepts. Before we go ahead and talk about its x-intercepts and other key features of intercept form, I want you to first look at A. A in your intercept form is very similar, or shouldn't say very similar, is the exact same A value that you have in standard and vertex form. So A previously and still, if it's positive, if it's greater than 0, the parabola is going to open up. So that's still true. And if A is less than 0, then the parabola is going to open down. The other feature that A still tells you in intercept form, if you think about it in terms of its transformations of a parent function, is A is still going to determine whether your graph is wider or narrower than its parent function. So if you recall from vertex form, if the absolute value of A is greater than 1, then the function is going to look narrower than its parent function. And if the absolute value of A is between 0 and 1, it's going to look wider than its parent function. So if we want to go ahead and find the x-intercepts, remember x-intercepts are when the graph hits the x-axis, and so to do so, y or f of x has to equal 0. So you go ahead and set f of x or y equal to 0, and you solve using the zero product property, and we'd have x minus p equals 0, so x equals p, and x minus q equals 0, so x equals q, and so p and q are just variables that they're calling to represent our x-intercepts. The axis of symmetry, since quadratics and parabolas are symmetrical, the axis of symmetry is halfway between the x-intercepts. And remember, the axis of symmetry for a quadratic function is the x-coordinate of the vertex. So if we want to go ahead and find the x-coordinate of the vertex, then we're going to take p and q, our two x-intercepts, we're going to add them together and divide by 2. Once we have the x value of the vertex, we can go ahead and take that, plug it back into the original equation, and solve for y. So on the next slide, we're going to use these key features to go ahead and graph a quadratic function in intercept form. So here in example 1, we have y equals negative 2 times x minus 3 times x plus 2. So notice this is still your example 1 on your guided note sheet. So I want you to fill in the key features as we move along here. And so the first thing we're going to want to look at is the fact that this is a negative 2 for an A. And so we know our quadratic, our parabola, is going to have to open down. That's a good thing to identify in the beginning, just like with standard and vertex form, because you can kind of tell if you're making an error if you start to plot the points and it's not going in the direction it should be. Notice this 2 also is going to tell us that at the end, if we were to put the parent function on the same coordinate plane, it is going to look narrower than the parent function. All right, so the first thing we need to find are the x-intercepts, because that will then help us find the vertex. So we're going to set y equal to 0 and solve for x using the zero product property. Now recall zero product property from earlier in the unit, that if I take 0 and I set it equal to negative 2, that's a false statement. So that negative 2, that GCF factor, gets thrown out. So really what I have is x minus 3 equals 0 and x plus 2 equals 0. So x equals 3 and x equals negative 2. And now we're going to use these values to go ahead and find our vertex. So the vertex is directly in the middle of those x-intercepts, halfway. So we're going to take the two x-intercepts and divide them by 2. So we'll end up with 1 over 2, or a half. And now that we have that x-coordinate of the vertex, we're going to take the 1/2, we're going to plug it back in for both of the x's in the original equation, and we're going to solve for y. So we have y equals negative 2 times, and again, I would simplify the parentheses first. So 1/2 minus 3 is negative 2.5, or negative 5 halves, and 1/2 plus 2 is 2.5, or positive 5 halves. So when we go ahead and multiply this all together, we get positive 12.5, or if you left it in fraction form, 25 halves. And the last thing we're going to want to find is the y-intercept. So the y-intercept, remember, is when you hit the y-axis. To hit the y-axis, x must be 0. So we're going to plug in 0 for both of our x's. So we'll have negative 2 times negative 3 times positive 2, and we'll get positive 6 times 2, or positive 12. So right now we have 4 points that we can go ahead and start to graph on the next slide here. So first we're going to want to plot our x-intercepts, which were -2, 0 and +3, 0. We're going to want to plot our vertex, which was 0.5, 12.5. And we're going to want to plot our y-intercept, which was at 0, 12. So right now we have 4 key points. As we discussed when we did standard form and vertex form, the goal is to try to have at least 5 key points. Sometimes the key features will only produce 3 points for you. And we saw different scenarios of that when we were doing standard and vertex form. But right now, since we have 4, we can easily reflect our y-intercept, if we have one, across the axis of symmetry. So on the next slide, we're going to go ahead and sketch the axis of symmetry, which recall goes right through the vertex, the x-coordinate of the vertex. So we have x equals 0.5 as our equation for the axis of symmetry. And so if we are a half a unit away from the axis of symmetry on the left side, then a half a unit away from the axis of symmetry on the right side will be our reflected point, which can be at 112. And once we have these 5 points, we can go ahead and sketch a smooth curve through those points and make sure that it looks like a U-shaped curve. And remember, the A value we stated in the beginning was -2, and so notice your graph is opening down as it should be with a -A. All right, let's go through one more example together on intercept form. So let's repeat this same process. So we have y equals 4 times x minus 1 times x plus 3. So a is equal to 4, which means our parabola is going to open up. Since the absolute value of a is greater than 1, that means that we are going to be narrower than our parent function. So again, properties that we've discussed throughout this unit when we were talking about vertex form and even standard form. And then if we go ahead and solve for our x-intercepts, you're going to set y equal to 0, and your p and q, and you might be able to do this visually, is just using the zero products property. So if I take x minus 1 and set that equal to 0, I get +1, and they're just using p to represent one of the 2 x-intercepts. So it's just a variable. And then x plus 3, if I set that equal to 0 and solve, I get -3, which we're just going to call q, just to keep up with the equation format for intercept form. So our x-intercepts are going to be 1, 0 and -3, 0. And utilizing those, we're going to go ahead and find the vertex by adding 1 and -3 together and dividing by 2. And so our x-coordinate of our vertex is -1. We're going to take that -1, we're going to plug it back in for both of our x's in the original equation. And we're going to start by simplifying the parentheses first. So we have 4 times -2 times +2, or -16. So the ordered pair of our vertex is -1, -16. So there's 3 points for us right now. And the last thing we're going to find is the y-intercept by plugging in 0 for x. So we end up with 4 times -1 times +3, and we end up with -12. So we're going to graph the 4 points that we just found on the next slide here. So our x-intercept -3, 0, the other one at 1, 0, our vertex at -1, -16, and our y-intercept at 0, -12. And now we're going to go ahead and sketch through the vertex our axis of symmetry so that we can then accurately reflect our y-intercept. So our axis of symmetry is at x equals -1. And so if I am 1 unit away from the axis of symmetry on the right side, then I can reflect that point 1 unit away across the axis of symmetry on the left side, which gives us a new ordered pair of -2, -12. And now that we have these 5 key points, we can go ahead and sketch a smooth curve here. And notice too that this is looking narrower than the parent function. Although the parent function is not graphed on this same coordinate plane, you can envision that it does look skinnier or narrower because again, that a value is greater than 1. All right, so now it's time for you to complete the following examples on your guided note sheet. So first you want to make sure that you have what we just discussed in the previous slides filled in there. And then you're going to try the next 3 examples on your own by first finding the key features using the same steps and sketching a graph of the parabola. After you go through those 3 examples, I want you to answer the critical thinking questions to the best of your knowledge. And again, these are things that you should be able to have some sort of thought about based on the fact of the work we've done with standard form and vertex form in the previous days. So I want you to try to think about these questions and write down anything that you think pertains or answers the question, and we will go over these at the start of the next class. So bring your questions to the next class and your thoughts, and we'll go over them. I look forward to seeing you all then. Bye now.